Now this will be our third example for refrigeration. Now the questions here. A commercial refrigerator with refrigerant R134A as the working fluid is used to keep the refrigerated space at -30 degrees C. By rejecting it waste heat to the cooling water that enters the condenser at 18 degrees C. So that is the condenser inlet, and it is a water-cooled condenser, so with water going in at 18 degrees C and leaving at 26 degrees C. Okay, so a mass flow rate of water here is given in the question as 0.25 kg per second. So the refrigerant enters the condenser, okay, at 12 bar and 65 degrees C and leaves at 42 degrees C, leaving the condenser at 42 degrees C here. The inlet state of the compressor is estimated to gain a net heat of 450 watt. So I have this Q in here actually is equals to 450 watt from the surroundings. Now find or determine the quality of the refrigerant at the evaporator inlet. That means the quality of the vapor refrigerant here. That means the dryness fraction. Now B, the refrigerated load. So that means the RE, the refrigerating effect, or the Q absorption. Okay. So C, the COP of the refrigerator, and D, the theoretical maximum refrigeration load for the same power input to the compressor. So this maximum refrigeration load, you have to calculate it based on the COP of a Carnot cycle. So now this is the TS diagram that I've shown here. Okay, so now how we got this line 1 to 2 prime here. In the later part, we will explain on this. So all this you have to refer to your property tables in order to determine your 2 prime. So we know that point 1 to 2, the S1 should be equals to S2. So if let's say S2 prime or the S2 at this point prime here is greater than what you have at point S2, point 2, then okay, you have the loss, okay, or the gain of heat that is due to this, okay, from the surrounding. So the compressor have to work much harder. Okay, so based on this part, and here you have undercooled 3 to 3 prime, and then 3 to 4 here, 3 prime to 4 here is where you have your H3 prime is equals to H4. Okay, so and this is the schematic diagram we have. So very simple, just find out the H1, H2, H3 and H4 at all the points that is shown in the diagram just now, then on the TS diagram or based on the schematic diagram. So based on the schematic diagram, as you can see, the inlet here is 0.6 bar and -34 degrees C. Okay, and then the outlet of a compressor is 12 bar and 65 degrees C. And then the outlet of the condenser is 42 degrees C. So based on this, actually, you can find out the enthalpy at H3 and then equate to H4. So you will be able to find out that 0.4 as well when you know the pressure here is 0.6 bar. Okay, so 0.4 and 0.1 actually should be at the same pressure line. Okay, 0.2 prime 2, okay, 3 should be at the same pressure line as well. So state point 1, so superheated vapor R134A at 0.6 bar and -34 degrees C. So you have to refer to your property tables for this, and why it is superheated, then you have to look at your property table. So at 0.6 bar, what is the actual saturation temperature? The actual saturation temperature should be at 0.1, yeah, at -36.45. Okay, so if it is at negative 34, that means point 1 is automatically superheated. Okay, so that is higher than negative 36.45. Okay, that is your negative 34. How you got negative 36.45? That is by referring to the pressure of 0.6 bar. And how you get 46.29? That is by referring to the pressure of 12 bar. That is your condenser pressure, and this is your evaporator pressure. Okay, so we can find out the enthalpy is equals to 230.04 kilojoules per kg for superheated from the property table. Okay, now then state point 2, okay, is superheated. Definitely is superheated because point 1 itself is already superheated. So point 2 definitely will be superheated. So you check with 12 bar and 65 degrees C and try to find out your H2, or your H2 prime. It's actually your H2 prime. Okay, so T2, that is equal to 65 degrees C, and this should be H2 prime. Okay, sorry, this is again another error, a slight error here. Is equals to 295.18. This is H2 prime. I repeat, H2 prime. Then take point 3. Okay, we know that undercool R134A at 12 bar and 42 degrees C. So you can check 12 bar with 42 degrees C. So we refer back to the diagram, sorry. Okay, so this is 46. Okay, so the saturation temperature at 12 bar is actually just now what we have got. Okay, 42. So that is why it is being undercooled. So it is 12 bar. What we have at 12 bar is 46 point something. And given the question is 42, so that means it should be undercooled. So based on the pressure of 12 bar and this temperature 42, you should be able to find out your H3 prime. Okay, actually this should be H3 prime as well. Okay, sorry, correction here again, H3 prime. So that is 111.25 kilojoules per kg. Then take point 4, which is equals to the enthalpy at point 4 should be equals to the enthalpy at point 3. That means it should be equals to 111.25 because it's a throttling process. Okay, so that is at pressure 0.6 bar. So we got H3 prime, H3 prime actually, H3 prime, not H3. H3 prime is equals to H4. So and from here we can find out the quality of the vapor, not steam, sorry. It is the vapor refrigerant R134A. So this is the dryness fraction or the quality of the vapor refrigerant. So based on the liquid enthalpy of water, because from the earlier diagram you can see that condenser, the water going in is at 18 degrees C and leaving at 26 degrees C. So at 18 degrees C, based on water, this is not refrigerant. Okay, going into the condenser, because the condenser is a water-cooled condenser. So they're using water, cold water, to condense the vapor refrigerant. So therefore, you have to refer to at 18 degrees C for water, so that is HF. So you get 75.47 kilojoules per kg. And for 26 degrees C, you have this. That is also water. So it's 108.94. So from there, based on the energy balance, we know that the condenser that we use here is a water-cooled condenser. Inlet is positive 18, outlet is positive 26, that is for water. On the refrigerant side, the inlet is at a temperature of 65. Okay, at temperature of 65 degrees C. So take a look at this diagram here. Inlet refrigerant is 65, outlet is 42. This is 18, this is water. But when we have already got the enthalpy for this and the enthalpy for this as well for water, and then the enthalpy for this and this as well, 12 bar at 42 and 12 bar at 65. So we have found out both the enthalpy as well. So therefore, we can use actually the enthalpy based on the energy balance. Okay, based on the energy balance. Okay, to calculate the mass flow rate of the refrigerant M dot R. Why do we need the M dot R? Because we have to calculate the rate of heat transfer and power. So mass dot W here, M dot W here is actually referring to the mass flow of water, and it is also given in the question as 0.25 kg per second. So we have actually found out the H2 and H3. HW2 and HW1, we have already found it by referring to 18 and 26 degrees C for water. So from this, you will be able to determine or find the mass flow rate of, actually it's the mass flow rate M dot, M dot subscript R. The mass flow rate of refrigerant is 0.0, not comma, 0.04549 kg per second. Okay, then from that, you will be able to find out, the rate of heat rejected, by multiplying it with mass flow rate of refrigerant, and then you will be able to find out the power input. So that is the rate of heat rejected, and this is the rate of work input, that is the power input. Okay, so based on this, the energy balance again, so this is an energy balance. We know that the energy input to the cycle, you have work in, you have the Q in, that is from the surrounding 150 watts that is given in the question, and this is the heat absorption. These are the three form of energy. These are the three energies that go into the system, and this is rejected, that means leaving the system, leaving the cycle. So you have this. When you manipulate this, you got this. Actually, your heat absorption here, the rate of heat absorption is actually your cooling load or your refrigeration load, or we can call it as the refrigerating effect or heat absorption sometimes. So by putting in all these values here, you will be able to find out the rate of refrigerating or the cooling load. That is 5.404 kilowatt. Okay, so the COPR, for refrigerator. So you will be able to find out COPR, that is the coefficient of performance for the refrigerator, as 2.15. And then the last part of the questions, earlier they have said find out the maximum what is that? We will refer to the question later on again. COP, this subscript C here stands for Carnot cycle. So for Carnot, reverse Carnot cycle, we have the COP as this. So the TL and TH is taken with respect to the saturation temperature at the base, both on the evaporator pressure and on the condenser pressure. So by putting it in, you will be able to find out the COP maximum actually. So that is 2.859. But so as compared to this, you can see for Carnot, reverse Carnot cycle, the COP should be higher than the refrigerator, the actual simple vapor compression cycle. So based on this, so you will be able to find out the maximum rate of heat cooling load, the maximum cooling load required. The question asks us to find maximum cooling load. So this is the COP max that we have, multiplied by work in, because we know that COP is defined as RE over work in. So when you manipulate the equations, you got this. So from here, that is your final answer, 7.18 kilowatt. That is for the maximum cooling load. Thanks for the listening, or viewing. So if you like the podcast, please subscribe and view and like, please. And then if you have any comments, you can place it in the comment section. I will come back to you as soon as possible. And this will wrap up the chapter on refrigeration for the diploma level. So later, maybe next year, I will proceed with the degree level. Thank you very much. Enjoy your evening. Thanks a lot. Bye-bye.